MongoDB has been working toward distributed transactions over the course of the last 5 years, ever since MongoDB 3.0 and the introduction of the Wired Tiger storage engine. Over the last several years, some notable milestones have included the global logical clock, Wired Tiger timestamps, and of course, replica set transactions. In MongoDB 4.2, MongoDB now coordinates a commit across multiple shards, or partitions of data. To deliver this functionality, we introduced both a distributed commit protocol and a new document state, the prepare state. Now, a distributed transaction can contain any number of operations across any number of collections across any number of documents. The data you touch in a transaction could live on any shard. So let's say we're doing 2 updates across 2 shards. In order to maintain the atomicity or all-or-nothing execution of those writes, MongoDB needs to coordinate the commit across nodes. Additionally, it's impossible to see the uncommitted writes of in-progress transactions, meaning writes on any single shard will only be visible once they are guaranteed to be committed across all shards. Let's define some terms. First up, participant shard. A participant shard is any shard that served either reads, writes, or both for a given transaction. This makes a shard a transaction participant. Read participants, participant shards that only service reads for a given transaction, also participate in the distributed commit because they must confirm the data read was majority committed before returning success. The next term to discuss is coordinator. The coordinator shard is selected among all the participants in the transaction. It is the coordinator's responsibility to manage the distributed commit protocol for a given transaction. Now that we have those terms defined, let's talk through the workflow of a distributed transaction that spans shards. First, the application must open a session and start a transaction on that session. Then the application performs CRUD operations within the transactional session. In this case, let's say the application sends 2 inserts across 2 collections across 2 shards. Those 2 shards are participant shards for the transaction. One of those 2 shards is the coordinator for the transaction. When the application sends the commit message, the coordinator sends a prepare message to all participants, including itself. When a participant shard has successfully prepared their uncommitted writes, it has promised that it can commit the transaction's writes, and that promise has been replicated to a majority of nodes, so the promise will not be lost. All documents that have transactional writes prepared will not be able to service any writes or reads with high consistency levels, like linearizable, causal consistency, snapshot, including transactions, until the transaction completes, by committing or aborting. If the coordinator receives some failures from the participants on the prepare attempt, or if the coordinator times out waiting for the specified max commit time MS, the coordinator will abort the transaction everywhere. If every participant has successfully prepared, meaning every shard has promised to commit the transactional changes atomically, then the coordinator can send a commit message to each shard. Once the commit is processed, the documents can start accepting all reads and writes again. Our transaction has been committed. Imagine having to write that logic yourself in your application. MongoDB handles the complicated distributed systems problems for you, so you can focus on what matters most, your application features.